Can you hear me now? Okay, good morning, everyone. Welcome to this problem-solving webinar hosted by Oxford University Press in consultation with AMESA. My name is Sharon Billett, and I'm representing Oxford University Press in my capacity as mathematics and science publisher. I'm also joined by my colleagues, Michelle Sefton, who is the content specialist for mathematics and science at Oxford University Press, as well as Danielle Carls, who is our marketing specialist. There may be other OUP colleagues that might join us or that might already be in the audience. So to you, welcome as well. And then also a big welcome to Professor Rajendran Govender, who is the Deputy Dean of Teaching and Learning at the Faculty of Education, School of Science and Mathematics Education at UWC. Welcome, Prof. And then, of course, to our presenters, Tatiana Sango, as well as Sanet Steyn, who will shortly introduce themselves and who will basically be doing the presentation or the webinar for this hour. Just three things quickly I want to request from you so that our webinar runs smoothly this morning. Firstly, if you could turn off your video if you have your video on. Secondly, if you could mute your sound so that we don't have any background disturbances on the audio. And then lastly, we will have 10 minutes at the end of the webinar for questions. So do jot them down while we're in progress for the Q&A at the end. So that's it from me. Over to you, Tatiana and Sanet.
Apologies, I can't seem to unmute once I'm in presentation mode. So I'll start now. You can see my screen, right? So there are two presenters for you today, myself, Tatiana Sango, and Sanet Steyn, who will introduce herself. I am a mathematics research lead in CETAP at University of Cape Town. And my professional career ranges from teaching and learning to publishing and e-publishing. Prior to joining CETAP, I worked at Pearson South Africa, and I worked on development of learning, teaching, assessment materials across mathematics, science, and e-learning. My current interests are in mathematics assessment, item development and design, as well as the assessment delivery modes.
Good morning, colleagues. My name is Sanet Steyn. I'm the Academic Literacy Research Lead at CETAP. I work with Tatiana on the MBTs. My background is in applied linguistics, and my research interests have been focused on academic literacy for a number of years now. I've also worked in the teaching of academic literacy, and I'm currently involved in projects looking at not only the assessment of academic literacy across different language groups in multilingual contexts, but also applying academic literacy concepts to content-specific areas. Thank you.
We introduce our webinar objectives briefly. Academic literacy in school mathematics, in particular, calculus applications, will be discussed. We will reflect on NBT observations in relation to first-year studies. We will talk about rates of change in the South African CAPS curriculum and reflect on NSC reports specifically on rates of change questions, while analyzing 2016, 17, 2018, and 19 questions involving applications of rates of change. We will look at the problem-solving strategies and apply one of them to all the questions we discuss. We will also discuss further examples and show you some useful resources. The purpose for today's workshop is to look at the strategies of understanding and developing learners' reasoning when solving problems with rates of change. When we look at students' reasoning, we look firstly from the academic literacy perspective. Academic literacy, AL, refers to students' capacity to engage successfully with the demands of academic study in the medium of instruction within the educational context. To understand student reasoning, we must examine the academic demands of our course or subject, content from many different angles, and reflect on not only the more obvious subject-specific skills and knowledge areas that form part of students' conceptual understanding of a particular component of the subject, but also their abilities that are being used in the background, such as academic literacy skills. Research indicates that inadequate preparation in using academic language at school level specifically is an obstacle to learning for both monolingual and multilingual students with low language proficiency, especially with regard to conceptual understanding. Careful attention should be given to the specific academic language demands emerging during conceptual development in mathematics learning. So that would be throughout their school career of learning mathematics concepts. When we look at academic literacy skills and those that specifically at play in mathematics, we look at cohesion, communicative function, discourse relations, essential, non-essential distinction making, grammar and syntax, extrapolation, application and inferencing, metaphorical expression, text genre, and vocabulary. All those have a role to play when developing mathematical understandings. Some of them are more important than the others, and Sanet will discuss those for us.
Okay, so of these 9 skills, we're going to, or 9 subdomains, we're going to first focus on the 4 most important ones and that have the most obvious link to mathematics. So the skills of distinction making or essential, distinguishing between essential and non-essential, inferencing, understanding metaphorical expression and vocabulary are all typically used in all disciplines and are therefore relevant to a student's ability to understand concepts and complete tasks. But these 4 subdomains in particular play a big role in facilitating a student's understanding of concepts, interpretation of content, and application of content knowledge. Distinction making, for example, enables the student to sift through information and identify key facts and concepts. So eliminating what they don't need and to focus on only what they do need. Then in terms of inferencing and extrapolation, here the most obvious thing they need to do is to make connections between what they read in a scenario or an example and connect that to mathematical principles that are relevant or are at play. And they also need to be able to draw all the facts from what they see, whether it's explicitly stated or implied. And then the next 3 subdomains sort of work together. They are all related to understanding structure, sequence, and function. And in essence, these elements also feature in mathematical procedure. So you can say that these skills are a sort of proxy for that type of thinking, for being able to understand what makes up an argument and understanding how to present evidence to come to a conclusion, which would be very similar to solving a problem or to explaining a proof. And then lastly, we have 2 more subdomains that are not as clearly linked to mathematical content, but if students have trouble with these, they might not be able to understand the scenarios that are sketched or the more lengthy explanations of concepts. So what happens here is that if they struggle with something such as text genre, they may miss slight signals that such as absolute values, etc., that are embedded in the language rather than stated in the way they might be used to it being emphasized in the classroom. So if we look at what we can see from the national benchmark tests, we do a subdomain analysis every year to see what the performance is like in the individual components of what we assess, and overall we see that the following subdomains sort of stand out as problem areas. Students seem to struggle with non-literal language use, as well as terminology and vocabulary items that they may not be familiar with. And they also seem to struggle with questions where things are not explicitly stated and where it requires inferencing. And in addition to these things that we see from the academic literacy performance, we can also see from quantitative literacy that the understanding change in rates, which is relevant to today's topic, is even difficult for them within everyday scenarios, such as those presented in the QL paper. We can move on, Tatiana. So if we look at the NSC diagnostic report, we've drawn some of the things that seem to be relevant to academic literacy skills, and if we were to summarize what we've seen from the 2017, 2018, and 2019 reports, we can see that there are a specific mention is made of students not being able to use the information that is within the question, or that they miss certain critical elements of the questions, or that they confuse phrases and words, and therefore do not then use the correct information when they proceed in their doing of the tasks. So if you can click, Tatiana. So in essence, learners are missing the signals in questions, so they're not picking up on those cues. They seem to have trouble with understanding and interpreting questions, and where language sort of hurdles come up, there seems to be quite a few examples of that happening. So in addition to the recommendation that these reports make that teachers expose learners to more higher order thinking questions, we also need to find out or find a way to anticipate where learners will need guidance, and also what type of guidance they would need. So in order to do this, we've come up with a way of looking at how a student goes through content, whether it is within the course structure, as in class content, or when they are dealing with tasks and assessments. And as they go through these steps of thinking, we need to keep asking ourselves, within this step, is there something that I need to do as a teacher to try and facilitate that process? Are there things that I can anticipate they might have trouble with? So if we look at course content, for example, the first part would be to read and analyze the content. They need to understand the key vocabulary items, pick those up, and then determine what the focus of the content is. The second part then would be that they need to make certain inferences. They need to determine what is new and what is based on familiar concepts, then understand how they differ and how they are the same from what they've just established. And then they must analyze the examples that are presented the way they would when they tackle a question for homework, etc. And the last step would be that they need to identify sort of the standard procedure for applying this knowledge. So take note of how examples are worked through, how the answers are presented, to understand what the typical format of the answers need to be. Now, when they analyze assessment tasks, this differs slightly. There's some changes to the first step here. They'd also have some initial extrapolation of information. Step 2 is a little bit different, because here, when they are essentially doing a task analysis, so they need to determine for every question, what is it that we know? How does this relate to mathematical principles and the concepts that they know? And then finally sift through everything they see in that question to drill down to only what they need in order to complete the task. And then finally, in completing that task, they need to apply that mathematical knowledge and follow the standard procedure, but also keep the sort of the prescribed format in mind of their answers. And I'll hand over to Tatiana now to do the rest.
Thanks, Sanet. So let's look at the CAP's interpretation of rates of change and where do they appear. In functions, we're looking at the main and range, intercepts with the axis, turning points, minimum, maxima, asymptotes, shape and symmetry, average gradient or average rate of change, intervals on which the function increases, decreases, and then directly in calculus, we have the two important bullets. An intuitive understanding of the limit concept in the context of approximating the rate of change or gradient of a function at a point. And the second one, solve practical problems concerning optimization and rate of change, including calculus of motion. So we're looking at the rate of change concept as one of the most important applications of the derivatives, and use the fact that the first derivative represents the rate of change of the function. It seems like a large number of students seem unprepared for calculus when we look at the MBT results and the first year results in engineering studies, in physics, chemistry, and so on. Many students need to be motivated to study and learn. Many students have misconceptions, and also the lecturers have expectations that the students come into their courses with fair understanding of what the rate of change is. So the most important, we would identify 5 most important prerequisites, concepts that calculus students must understand. Algebraic fractions, functions in all their properties and glory of properties, exponents, inequalities, solving trigonometric equations. And mastery of these concepts found to have more than double the impact of taking a calculus course successfully later on in their performance in the first year studies. So let's look at the different types of problems that relate to rates of change and calculus of motion. So first one that I have, I don't know why I can't move this thing down, but it interferes with my presentation. I try, it keeps on moving. No, all right. So calculus, as we know, an advanced mathematics topic, and applications of rate of change are used in many courses beyond school mathematics. So I have divided this specific group of problems into 2. When we use calculus to describe a motion, that is the direct application of velocity, acceleration, distance. And by definition, we know acceleration is the first derivative of velocity with respect to time, and velocity is the first derivative of position with respect to time. And then the second type of problems, we're using stationary points of functions to maximize or minimize, which is already optimization type of problems, but in the context of physical quantities. The key vocabulary involved acceleration, average rate of change, instantaneous rate of change of f with respect to x at a point, speed, distance, tangent line, displacement, velocity, maximum and minimum. Those physical concepts are very important for the learner studies beyond school mathematics. And I'm going to be struggling with this little thing. Let me see. It does not want to go away. Apologies. All right, let's look at the first examples, average versus instantaneous rate of change. When we look at this example, what is important is for the learners to understand two concepts, mathematical concepts, the average rate of change and instantaneous rate of change, and draw the difference to actually understand deeply the difference between the two. So in this particular example, we have straightforward problem with not much context involved. The distance an object travels over time t is given by the function, where s is measured in meters and t is measured in seconds. So there is only one equation. There is a description of the two variables. The first question involves the average rate of change in the interval 0 and 2, and the average rate of change is given by the gradient ratio. We're looking here at specifically change in distance over change in time. And that would be familiar concept to a certain point to the students where they look for the gradient or the change in y over change in x. They're looking at the function substitution and finding the values, and you can see the answer is pretty simple for them to work out. And the rate of change in the distance s is -6 meters per second. Very important to always draw that conclusion, to answer the question, to go back to the question. When they write down that answer, it is a point where they reflect on their calculation and on the reasonable answer that they are giving. And then the second one, instantaneous rate of change, when t is equal to 3. So an instantaneous rate of change at a particular time, not in the interval. And to find the instantaneous rate of change of the distance, they're looking for the first derivative. So they need to differentiate. They need to then pick the time equals to 3, substitute and find the answer and draw a conclusion. The instantaneous rate of change of the distance at t equals to 3 seconds is -18 meters per second. And the second example that we look at now, this is velocity and acceleration. And again, this is not a very complex context, and we are looking at two very important concepts. One is the velocity and the other is acceleration and their relationship. The function describing the position of an object dropped from a height of 100 meters is given by this equation. S is measured in meters, t is measured in seconds. Find the object's velocity and acceleration, but now when it hits the ground. So there's the additional layer to the question. The learners would need to understand what really happens when the object hits the ground. Certain things that need to be explained in the context, maybe even drawing the diagram, but stop there. Not just tell them when it hits the ground, then we're looking at the velocity and setting the function equal to 0 and moving on with calculations. So first step is to break down what are we looking for. We're looking for velocity, and velocity is the first derivative of position, and therefore we find the first derivative. The acceleration is the first derivative of velocity with respect to time. Again, we find the first derivative, we calculate. Then to find the velocity and acceleration of the object when it hits the ground, we first find the time at which it hits the ground by setting the function equal to 0 and then solving it for t. And once the time is then found, we substitute to find the velocity. And there's need to be one step more to interpret what the acceleration is when it hits the ground. And obviously it is constant there, it never changed, and the object acceleration is the same, which is -9.5 meters per second, and it is due to gravity and is directed downwards. Seems my network is complaining. All right, now let's look at the type of questions in the National Certificate exam. On 16 to 20 different types of questions, specifically in context of change. I might not be able to cover all of them, but look at the method or the strategy in approaching those type of questions. So in 2017 November examination, we had the context, aerial view of a stretch of road is shown in a diagram. The road can be described by the function y equals to x squared plus 2, x greater or equal than 0, if the coordinates dotted lines are chosen as shown in the diagram. So diagram is given. Benny sits at a vantage point B with coordinates 0 and 3 and observes a car P at a particular point on the curve traveling along the road. Calculate the distance between Benny and the car when the car is closest to Benny. Many learners generally just, okay, move on, next question. So what do we suggest? We suggest that looking at the problems like these ones in 4 steps. The first step is to construct learners' understanding of the problem, looking at extrapolating information, inferencing, and developing reasoning. So the first thing is to forget about all the equations and numbers, etc. Try to understand the problem. So what do we know? Benny is not moving. His position is fixed at point B with coordinates 0 and 3. There is a curve, and the curve represents the road. Car is moving. Its position is described by the point P, which will be sliding on the curve or basically traveling along the road. The coordinates of point P are changing because the point is moving in the xy axis, but the point always remains in the first quadrant, which means your x and y coordinates remain positive. The distance between Benny and the car is not always the same because the curve is not always the same distance from point B on the y-axis. And that could be explained, it could be visualized that point P could have been on top of the curve, it could be further down, it could be lower, etc. And learners would need to understand that the distance is changing. The problem is asking to calculate the distance when the car is closest to Benny, or shortest BP distance. So all that, as much as you can list, as much as you can lift from the problem, would assist learners' understanding. And maybe that list would be different for different students. Now, in step 2, we suggest linking mathematical content knowledge and use of concepts, draw inferences, and select relevant information. So now that we have all the information listed in step 1, we can look at the relevant mathematical concepts. The curve represents the road and its equation is given. Great, we have an equation. Point P represents the car, but we do not know its coordinates. So there is a point P. It has coordinates x, y. Point P is on the curve. Car is on the road. So if point P is on the curve, now here we need to link how the y coordinate could be represented in terms of the knowledge of the given equation and how it could be found in terms of x. The distance between 2 points B and P, Benny and the car, is unknown. So here, the Q here is the distance. So the learners are expected to know the distance formula and apply it correctly. And it is between 2 points. So point P is the given one, point 0 and 3, and point P is the one that they have defined in the previous block. So P is x and x squared plus 2, and thereafter PB needs to be found, and these are the algebraic manipulations that learners need to be comfortable with. Now, the distance between 2 points has to be minimum. We're looking at the shortest distance. Here, students or learners need to realize that PB will be a minimum if PB squared is a minimum, because that will help them with the next step. Right. Step 3, we suggest completing the task application of knowledge and use of the correct argument format. So I remind you again, as step 1, they listed all the information they could possibly identify from the problem. Step 2, they needed to link the relevant information to the mathematical concepts. And finally, now they need to use more or less only the mathematical knowledge that they have acquired. So to find minimum distance, step 1 is to differentiate the given expression and find the values of x, where first derivative is 0. So the calculations they need to do, they have to differentiate PB squared and then equate it to 0 and find the two values of x. In this case, there are two values of x, and then make sure that they understand to choose the relevant information. Step 2, substitute the values of x into the distance formula to find the minimum distance. Again, algebra, and they substitute and define the distance PB equal to 0.87. Now, as before in the two examples, it would be good for them to draw a conclusion. So 0.87 units, they are now defined in this problem, is the distance between Benny and the car when the car is closest to Benny, so that minimum distance. Finally, the step 4 is more or less teaching step. It is important for the teacher to reflect with specific focus on potential problems in learners' reasoning. So that step could involve alternative solutions, it could involve common misconceptions, any difficulties that learners might experience, which will then allow the teacher to direct the learner to the relevant learning or intervention. So in this problem, the alternative reasoning could be constructed in step 2 and 3, but that would depend on learners' mathematical and cognitive abilities. So one of the possible solutions could have relied on the shortest distance will be where tangent to curve is perpendicular to the line joining P and the curve, and a second possible solution could be constructed when finding the equation of the line segment BP and working out the values of y at P, which would also take them to the same answer. The NSC report talks about the specific question and highlights common errors and misconceptions. So what happened in the first one, many candidates did not see this question as an optimization question. The most common incorrect answer was that BP equals to 1 unit. The other common mistake was to take random points for P and to calculate the length of BP. So clearly here they couldn't identify or define the coordinates of point P. Few candidates managed to establish that BP squared equals to the expression x to the power 4 minus x squared plus 1, or BP is a square root of that expression, but could not differentiate these expressions. So that is now the concept, lack of concept. Candidates did not realize that BP is a minimum if BP squared is a minimum. The majority of these candidates then use trial and error to establish the minimum distance of BP. Suggestion for improvement, again, those are general suggestions. Optimization should not only be seen in a context of measurements, learners also need to be exposed to optimization of functions, and especially in a context where something is moving, something needs to be visualized, interpreted. And the common complaint always is that this section of calculus is often taught towards the end of the year, and therefore learners do not get enough opportunity to practice. Teachers should ensure that there is enough time for learners to understand the application fully, although I know it is a very difficult ask of the teachers. All right, let's look at the other problem, but we will look at it briefly. 2018 November examination also had a problem in context. After flying a short distance, an insect came to rest on a wall. Thereafter, the insect started crawling on the wall. The path that the insect crawled can be described by this function h of t, where h is the height in centimeters above the floor and t is the time in minutes since the insect started crawling. So the questions are there: at what height above the floor did the insect start to crawl? How many times did the insect reach the floor? Determine the maximum height that the insect reached above the floor. Once again, we take the 4-step approach. The first step is to construct learners' understanding of this problem, extrapolating information, inferencing, developing reasoning. Here, one could even draw an insect which was flying somewhere, landed on the wall, and then what happens is that insect starts crawling up and down, creating some kind of a curve. But that's some kind of a curve, obviously the curve that is defined by the equation. So drawing a graph of that equation could have helped as well. Now, summarizing the information that learners could directly lift up from the problem, an insect is flying and coming to rest before crawling on the wall. So anything before that insect was flying is not important to this problem. Curve h of t represents the crawling path of the insect. Unlike in the previous problem where we saw the curve when the car was driving, here we don't see that curve. So that question is slightly, let's say, more advanced maybe, because it requires learners to do something to visualize. The starting position on the wall is the height h above the floor where insect landed after flying. We do not know in which direction the insect crawls, towards the floor or towards the roof, and it also changes direction. Now the problem is asking to find the height above the floor where the insect starts to crawl or where the insect lands. The number of times the insect will reach the floor, how high the insect will crawl. Probably more for some students, they might be able to find more information, but we are listing only these. Now, step 2, linking to mathematical content knowledge, use of concepts, drawing inferences and selecting relevant information. We could divide it into 3 big sections. The one is the insect lands on the wall before starting to crawl, which means that time starts at that point, which also means then that t equals to 0. The crawling curve's equation is given. Although the curve itself is not shown, the equation is given. It describes the height above the floor at any given time. The insect could crawl up or down on the wall, never reaching the floor or reaching the floor once or more than once. When the insect, however, reaches the floor, the height above the floor is 0. So some interpretation is needed. Therefore, h of t is 0. The insect could only crawl as high as the wall is, but will not necessarily reach the top of the wall ever. The maximum height that we're looking off of the insect describes how high that insect will crawl on the wall, and therefore we're looking for maximum height. And the maximum height is where first derivative is equal to 0. Looking at the third step where they can supposed to construct a solution and complete the task, we apply the knowledge and use the correct argument format. The initial height is when the time is 0. They should be able to substitute that 0 into the given function and calculate the initial height being 36. To answer the question, when will the insect reach the floor, is to find the time when the height is 0. Okay, when will the insect reach the floor? Meaning the height is now 0. So equating height to 0, they would need to solve the equation. Quite common, students start to multiply out and then getting stuck completely, not realizing that it is already factorized. So all they have to do is to equate each factor to 0. And then further, they will realize that this equation has no real solutions. So there is only one answer. Insect will reach the floor only once when the time is 6 minutes. Now to find the maximum height, we have again the 2 steps: differentiate the given expression and find the value of x where first derivative is 0, and work out and find the 2 possible answers, 4 and 1. In step 2, they substitute the values of x into the height formula to find the maximum height. Only t equals to 4 because height reaches maximum value at that time, and the height is 52 centimeters after calculations. Now, step 4, where we reflect on the problem with specific focus on potential problems in students' reasoning. As I mentioned before, drawing the curve was missing, so drawing a curve could assist with visualization and address some of the observed errors and misconceptions. That curve could be drawn with the help of graphical software, it could be drawn by hand, but it would need to be fairly reasonable in relation to the equation that is given. NSC report lists common errors and misconceptions in relation to this problem. Many candidates gave the answer as t equals to 6. They calculated the value of t when h is 0, instead of calculating the value of h when t is equal to 0. It indicates that students usually look for the procedure and apply any procedure that they remember from when they were engaging with typical problems. Many candidates confused how many times was at what time. in the question 8.2. They gave the answer again as t equals to 6 instead of indicating that the insect reached the floor only once. In answering the third question, some candidates could not correctly multiply out h of t. Some candidates calculated first derivative but did not equate it to 0. Some calculated the values of t but did not calculate the maximum height. Other candidates calculated even second derivative, equated it to 0, and solved for t, not realizing that in this way they will calculate the t value of the point of inflection and not the maximum. The suggestions for improvement here: when teaching graphs of cubic functions, teachers should also include those that have one stationary point. Teachers need to expose learners to word problems, and again, the calculations of critical values should not only be restricted to graphical questions. Expose learners to calculating critical values in the contextual questions as well, and this is one of them. Right. In 2016, the problem was slightly different. The number of molecules of certain drug or in the bloodstream T hours after it has been taken is represented by this equation. The interesting play of the questioning first was determine the number of molecules of the drug in the bloodstream 3 hours after the drug was taken. So that's common. Second one, determine the rate at which the number of molecules of the drug in the bloodstream is changing. So rate at which it's changing it's at exactly 2 hours after the drug was taken. How many hours after taking the drug will the rate at which the number of molecules of the drug in the bloodstream is changing be a maximum? So again, we took the 4-step approach. I'm not going to discuss it in much detail, otherwise I will run out of time completely, but you will have these slides as well as the worksheet to engage with. And the common errors listed: many candidates did not see the connection amongst rate of change, gradient, and derivative. Hence, it was evident that the candidates did not link maximum rate of change to the second derivative being equal to 0. And so on. Now, the other type of problems, which is more common, rates of change and optimization problems. However, learners often experience difficulties in this topic. One of the main reasons for this is the ability to understand the wording of the problem. The difficulty often arises when identifying the quantity that is to be optimized and the quantity that is the constraint, and writing down an equation for each. Here, maximize, minimize, optimization, and the constraint play a role. Let's look at the example from the Zoom in Mathematics title. And the optimization problems will always ask you to maximize or minimize some quantity described in a word problem, instead of immediately giving you a function to maximize or minimize. So, for example, keeping the area of the rectangle fixed, which rectangle will have the smallest perimeter? So we suppose our rectangle has area 15, the perimeter of rectangle is given by the formula, and our constraint is that the area A equals to xy equals to 15. So again, we look at the 4-step approach. There is no real difference, although there is not that much context, but it is still useful constructing learners' understanding of the problem. And here, the two most important points. We're looking at the quantity to be optimized, which is the perimeter of the rectangle, and the quantity that is a constraint, which is the area of a rectangle. Then linking to mathematical content knowledge and using the concept, we're looking at perimeter, which is to be minimized, bringing in the formula now into the second step, and area of the rectangle, bringing it in is the constraint. Then being able to rewrite the constraint equation and substituting it into the quantity that is to be minimized, finding the expression for perimeter. Then completing the task application of knowledge and use of the correct argument format. Again, we taking the derivative and we're working through the usual steps to lead the learner to the answer. Okay, I'll need to... So here in teacher reflection with specific focus on potential problems in students' reasoning, it might be in the form of intervention. And sometimes it is helpful to show them some visual help visual give them visual assistance. So I'm using the Oxford University Press Zoom in Mathematics to show you some of the examples that could, if I can just get there, it's giving me a bit of a problem. Sanet, maybe you could play and present, because it was giving me problems this morning.
I can do that.
Okay. Do you want me to stop presenting and you can then
yes,
take over?
Please. I hope everyone can see. So, Tatiana, you'll just direct me through this?
Yes. So basically, carry on until we find that example. Yeah, carry on. This one. If you can play it, please. No, next.
There we go.
Play. There we go. So this one is just giving few, not necessarily conceptual, but the concept development steps that are important to test that the learners understand. So if there were difficulties in optimization problem, you are looking at understanding where that difficulty or where that misunderstanding could lie. So the first question, go back. The first question. No, the first you click play. If you click play, then here we go. So for optimization problems, we first need to identify what needs to be minimized or maximized, as well as they. So this then indicating that they need to identify, right? So it's something to be minimized or maximized, and the constraint that they're looking for, instead of answering randomly. There we go, correct, the second one. So simple example, given a parabola minus x to the power of 2 plus 8, to find the maximum area of a rectangle inside the parabola, the constraint is given by. So there they need to be looking at the correct formula for the rectangle. Okay, on. Given a parabola, which equation needs to be maximized to find the maximum area of the rectangle inside the parabola? So that you can just click through. I just want to show the type of questions. Oh, so it's clicked anyway. So it's okay. I can move on. That's fine. All right. So sometimes just unpacking and being able to understand what it is and where the problem lies is what we mean by reflecting on the students' understanding of the problem. So now I need to go back and present from current slide. Okay, and that leads us to another type of question in, again, NSC paper 2019 June examination was very similar to the example we just showed you. So here, instead of perimeter and the area at play is the volume of a sphere and the volume of a cone. That diagram helps here, of course, because the cone is inscribed inside the sphere. Calculate the volume of the sphere. First question. Second, show that the r squared is equal to 64 minus x squared, and determine the ratio between the largest volume of the cone and the volume of the sphere. And once again, breaking it down into 4 steps, we can first construct learners' understanding of the problem by looking at the sphere, at the cone inside the sphere, and listing everything that we could possibly list. The interesting point here, the radius of the sphere is not necessarily the same as the radius of the cone, because when you're looking at the formulas, the r is present in both of them, so confusion might arise that the radius is the same value which they would use. Okay, constructing the solution again. And the teacher reflection here, we could look at familiarity with the properties, characteristics of cons and spheres, connection to content knowledge, not just the formulae. The common error might be confusing radius with diameter, although the visual aid helps mitigate that, or confusing the two radii, as I mentioned. The term inscribed may be problematic for some. Again, the visual representation helps. As we have seen with other questions, students may not notice the stipulation that the ratio is between the largest volume of the cone and the sphere. So I summarize quickly problem-solving strategy. Step 1, construct learners' understanding of the problem. Step 2, link to mathematical content knowledge, use of concepts. Step 3, completing the task, application of knowledge and the use of correct argument format. Step 4, teacher reflection with specific focus on potential problems in students' reasoning. And just two more points actually. Some considerations when teaching rates of change. When teaching applications of the derivative, it is important to focus on the interpretation of derivative as the rate of change of the function. And here the 3 points are quite important to move from one to another. The amount of change of f of x needs to be understood very well. Over the interval is the change in y values of the function, and there you have it. The average rate of change of the function f of x over the same interval. There you have it. Instantaneous rate of change is now the derivative, and in this case it is great to introduce the limit because this is the development of the instantaneous rate of change. The types of problems could be rates of change with respect to time, rates of change of quantities, maximum minimum problems, and the one distance, velocity and acceleration problems. Also, there's some of the resources that might be helpful to you when teaching and preparing for teaching rates of change. The past exam papers, you can find them there. NCS reports, you can find them there. NBT reports, you can find them. Teaching mathematics, connecting ideas, very nice resource, underground mathematics, Oxford University Press, you can find Zoom in. The one tool that I found useful personally, Desmos Online Graphing Calculator, good with visualization, some videos on Khan Academy, and some other topics on differential calculus from Ciavura. And that is the end of my presentation. Thank you very much. We can take questions.
Thank you very much, Tatiana. We open the floor for questions. We have a few